just reviewing what we did here, right? We started with our circle again, 12 up here and so forth, and we estimated the coordinates of this point, okay? And we figured, well, that's 0, 10, that's pretty easy, right? And we figured that 0, negative 10 would be 0, negative 10 would be here. Everybody understands that, okay? Then we estimated the coordinates of these points, okay? Estimated. Some people use what they know about trigonometry, which is good, but that's not an estimate, okay? You get exact values that way, or many decimal approximations if you use that bleeping calculator, okay? Which is a great thing, but that's not what we're looking. We're trying to get a visual understanding of how these numbers change, okay? So what we do is we make these estimates. Now, we used 310 as an estimate here, 95 as an estimate here. And it's clear how we estimated. Like on this one, I actually drew the projection lines. Now somebody else added this and an explanation here with cosines and stuff like that, and that's good, okay? But not everybody knows trigonometry, and we're not going to teach everybody trigonometry, okay? We are going to look at a couple of trigonometric functions, though, the basic ones, because they're part of the picture of the basic functions that I want you to carry out of here, because they're the functions you do almost all mathematics with up through the middle of, say, an engineering or physics degree. You know, up through your sophomore year, you're dealing with these functions. And we want to understand these functions in ways that you won't understand them, most likely, the way they're taught, and often the way they need to be taught in the classes you're going to have. We want to move a little deeper than that. Okay, so, okay, the 9-5 point, let's test that to see if it makes sense, okay? Now we know this circle has radius 10, so this distance has to be 10, and that's a hypotenuse of the right triangle that got drawn here, right? So we draw that right triangle here again and label the sides, and what has to be true if these are accurate. And of course, it's impossible to estimate them with complete accuracy, but the square of this plus the square of this has to equal the square of this. That's your Pythagorean theorem. That's just something you've got to always know, because you'll never get away from the need to know it and be able to apply it when you need it. So there it is, Pythagorean theorem test. We just do 9 squared plus 5 squared equals 10 squared. We find out that comes pretty close, which means that that's a, for at least for this point, it's a fairly plausible estimate, right? At least as far as the Pythagorean theorem test goes, okay? Now there's another one, somebody estimated 310 on this, okay? As far as the Pythagorean theorem is concerned, that's not bad, because 109, 100, square root of 11 is 111, so the square root of 109 is most likely closer to 10 than it is to 11, okay? There's some concavity to that curve, as you find out if you do the thing I asked you to do over the weekend, but missed the links or whatever. Okay, so that's all good. Now, if we want to get an exact value of this thing, and this is just a review of basic geometry, okay, we don't use magic, we don't use formulas. We take a circle, and we know if we put 12 o'clock here, 2, 4, 6, 8, 10, all these sectors of the circle will be identical, which means that all the triangles that we've divided this, well, all the sectors that we've divided the circle into are going to be identical, which means that this triangle is going to be identical to the triangle we get for any other sector. Now, the main thing we need to see is that this angle in here, there's 6 of them all the way around the circle. It follows immediately that you have 60 degrees in that angle. And we could do this without talking about degrees, symmetries, and so forth, but you don't want to go too deep on you right here. So we have these angles. This is an isosceles triangle because these are both radii. They're equal. So being isosceles with a 60 degree here, we very easily conclude that all the angles are 60. This is an equal angular or triangle, which means it's also equilateral. Just again by symmetry argument that you should understand from geometry, but since geometry is taught to people who are probably too young to understand geometry very well, in a class of people, most of whom don't really care, you know, you want to go a little deeper in geometry, okay? So half of this triangle then has dimensions 10 and 5, has leg, hypotenuse 10, one leg is 5, right? And this is a right triangle. If you cut this in half, you can do a geometric argument if you know how to do that. You should be able to. It follows then that this squared plus this squared equals 10. So if we call this thing x, x squared plus 5 squared equals 10, solve for x. People did a great job. Got square root of 75, which is 5 times the square root of 3. Okay? And you can work that out. You find it's between 8 and 9. And you just do square root of 75. You know, square root of 75 has to be between 8 and 9, since 8 squared is less than 75, 9 squared is greater. 75 is closer to 81 than it is to 64, and besides, the curve of a squared function is concave up, which means you're going to be significantly closer to 9 than you are to 8. When you do this, turns out it's about 8.7. Your calculator gives you a bunch of decimals, but that's not an exact value. And the exact value, as I said, is going to be 5 times the square root of 3. Okay, well, okay, that's good. Now we took a break. Then we came back and we estimated the x and y coordinates for t at the time, you know, the number on the clock we'll call t. Okay, that number on the clock is 12, 1, 2, 3, 4, up through 11. We estimate the x and y coordinates. People came up with reasonable estimates, and it took a little while, but it was worth the exercise. So people then did graphs. I asked for a graph of y versus t. Okay? Well, that graph is the purple one here, and people had no trouble making it once they actually heard what I said and didn't do y versus x or something like that. Okay? And if you did y versus x, well, I'm going to do that one for homework if you haven't already done it. It looks like this, and that's what people got. People got this graph, at least up to here, you know, they didn't extend it beyond, okay? And then people got this graph. Your estimates worked out fine. You got the basic shape of what you call the sine and cosine functions, okay? Made a couple of other observations. One is that every point of this graph is this far ahead of every point of this graph. Every point of the orange graph is this far ahead of every point of the purple graph, and I'll ask you to, look at your graphs and kind of verify that that's the case and how far ahead and how far behind. Then you got this little thing that I just threw in as an aside. E to the ix is cosine x plus I sine x. I mentioned that if you are 2/3 of the way through an engineering calculus course that's on track to do the things that engineering calculus courses usually do, you get Taylor series. And you know enough about how to do derivatives and stuff that Taylor series for the exponential function or the sine function or the cosine function are very easy. Okay, because there's a cyclical series of higher and higher derivatives, but you don't know what that means. And you can separate out the function for e to the ix, I being the square root of -1 imaginary number. Okay? Now you can separate it out and you get this, and it's really pretty easy. Also, e to the I pi equals 1. I mentioned Kahn because one of my favorite things I've ever seen Kahn do, I saw this when Kahn was just becoming Kahn. He's very new, when he first came on, 10 years ago or whatever. He did a video where he worked this out, and at the end he got e to the I pi equals 1, and his comment for that was, and if this doesn't blow your mind, you have no emotions. Said the way only Kahn could say it. He's pretty wonderful. So anyhow, that's just an incredible thing, as is this. And then even more incredible, exponential functions, exponential growth and exponential decay, and oscillations, which are basically governed by sine and cosine functions, are pretty much the most important aspects, model of the most important aspects of the universe. Everything from psychology, sociology, economics, up through physics, cosmology, chemistry, in biology, if anybody ever really learns to put it all together, because biology is a very complex system. Cells are very complex things. Okay, so that's all really important, and you're going to have problems that take off on these graphs, on which you did a great job. I also wrote down the functions. I kind of think without thinking too hard because I didn't get enough sleep last night, but functions, these functions are something very much like them. There's something wrong with that. You get pi over 6 times pi over 2, shifting it. But if that changes by 2 pi, I mean, no, I'm pretty sure that's close. Okay? And it's not hard to write them down if your head is clear and you have a minute to do it. Those are functions you could put into a calculator and they should look like this if I did it right, which I probably didn't. Okay? I just didn't want to take the time to check it out.